As welcome Dr. Jayanta Dutta, our today's speaker in the departmental seminar. So Dr. Dutta is basically a theoretical astrophysicist. So he works on primordial star formation with emphasis on numerical simulation. So earlier he completed his PhD degree from University of Evora, Portugal in 2016. Before that, he was in NCRA and IISc for a short period of time as a project student. So after completing PhD, he moved to Pisa, Italy, and he worked there as visiting scholar. Then he came back to India in 2016 in Aiza Mohali, where he spent for about 4 years. So currently, he is associated as visiting scientist in HRI, where he is doing research as well as teaching load here. So with these words, let us invite Dr. Dutta for his talk. Thank you.
Thank you, Professor Ramakrishna Das, for arranging my visit and arranging this talk. Okay, so let's start. So we are talking about formation of the very fast star or the fast source of light in the universe. The very fast source of light in the universe. Okay, so that is called the primordial star. So we will try to explain every term and their survival possibility. Okay, so let's start. So we should keep it in mind. This is a very fast source after the Big Bang. Okay, so if we just this is just to if we just see in the sky, night sky, there is a lot of astrophysical objects. For example, we have different colors, different structure, right? We know that blue are more the temperature is high rather than this red, and there is a like galaxy, different types of astrophysical objects, right? So of course it comes to the mind how this structure has been formed, right? If we just zoom in that part, this is a very few arc second. If you just zoom in that part, so just zoom in different type of galaxies, these galaxies, Andromeda galaxies. Okay, if you again zoom in, so there are from very large scale to small scale. The structure is highly nonlinear, right? There is a gas evolution, right? If we again zoom in, different type of gas evolutions come. So there is a like very active region is there, different colors. So you can see this highly nonlinear structure has a temperature evolution, density variance, right? The question is that how these things have been formed. Okay, so this is a very original picture, and you already know. So we are basically here at this point at the present time. The present time redshift is anyone? Zero, right? And if we believe this Big Bang hypothesis, we call it hypothesis because there are a lot of things still we don't know. If we believe this Big Bang hypothesis, which says that from this point, so there is a inflation. Okay, so we are not talking about these things because this is the like high energy people are doing this. So, for example, the expansion is very high there, and there is a universe is expanding as well as accelerating. That we know, right? So at this point, we can see there are a lot of astrophysical objects which we have just seen. But if we look back in time, we can see, and there are, for example, sun has a metallicity around 10⁻², right? And even in our chemistry chart, we can see there are a lot of chemical components, right? So from where all these chemical component comes, because in our cosmology course we have seen that primordial universe has only hydrogen, right? So from the hydrogen, so there must be some evolution. So all this chemistry of chemical composition has also been formed, right? So if you just look back in time, so of course the metallicity was very less. So so after the Big Bang, there is a dark ages, okay, and then the very first source of light, or the because only the when the star has been formed, then only it can radiate photon, right? So, we will be working on this area. So why? Because this is the kind of the so this actually connects this cosmology and this astrophysics. How from the one stars, how the galaxy has been formed, how the stars there is a a lot of other star has been formed. Okay, so that is called the so this happens the primordial star happens around 400 million years after the Big Bang. So which means at redshift around 18. So now the redshift is around 0. We will be working at redshift 18 or 20. Okay. The thing is that so we understand the importance, right? Because other if we for example suppose if a human being if his age is 400 years, if we can talk to that human person, we can know what is the situation of the area 400 years before, right? Exactly the this thing. If we can study this first star, we can know the situation when the situation of the universe when it was young, right? So and also it transforms the simple to complex universe. I mean, from here how the universe, all these astrophysical object has been formed. It also heated and ionized the IGN because once the radiation photon is coming, it ionizes the surrounding medium, surrounding the gas medium. So that's why it is important. And also the initial enrichment. I mean, from the poor metallicity, zero metallicity to there are lots of metallicity. Okay, so that's the now just to so if the Big Bang happens here after the dark ages, the very first source of light is also called the population 3. The very first source of light called the population 3, and the once the so here the redshift around 20 to 30, and it only hydrogen and helium, which means it formed within the atom only purely hydrogen and helium. When this population 3 starts evolve, then die, then maybe there is a supernova explosion. I mean, all the metallicity formed within the stars, it got into the supernova, and when the supernova from all the metal comes to the outside, right? So the next generation of stars is now polluted. So there will be hydrogen, helium, lithium, the others, right? So second generation of star is also called the poor metallicity or extremely poor metallicity, very poor metallicity, because the metallicity has now been increased, right? So that is weakly enriched heavier element. So that is called the population two stars. And again, when it forms die again the population monster, which is the present day star formation. The present day star formation like sun is a population monster. Although sun is kind of intermediate, but you can say so. This is actually so population three, then population two, population three, right? Okay, and this is the our present day universe. So this is around 13 billion years. Clear? So now the question is that now the of course there is no telescope which can study a star, which has been the telescope can, even the JWST, this can go say up to redshift 8, 10, right? But the primordial star form at 20. So of course, there is no telescope or no data analysis. So only thing is to do with some, take the Big Bang nucleus synthesis as an initial condition and use our physics like Boltzmann equations to simulate. I mean, through the simulations, right? So that is the only. So the questions we wanted to when and how did this cosmic dark ages end? Because it can give the idea. So this is not known. There are many things which is not known. How did the first source of light come after the cosmic dark ages? How did the first galaxy evolve? How did the metal within the stars to enrich this interstellar medium? How did the universe evolve? So there are these questions people are trying to answer from last 15 years. This is very new field. Only 15 years after the computer simulation after we have this computer simulation technique available. Okay, the only thing which is available that is CMB. We all know about the CMB, right? This is the oldest photon in the universe, right? From the last scattering surface. I mean, when the very first time electron and proton they combine to form the atomic hydrogen, then the photon can smoothly travel, right? So and that is the same, that is still there even here also. So that is only available. So we therefore need this high resolution sophisticated numerical simulation. Why you will understand why we need high resolution sophisticated numerical simulation to understand this dynamical process. So this is kind of the overview. So we already talked about that, and we will just go what kind of numerical simulation we do. Now, what can now how we will do that? The only thing we have available is the modern cosmological. This is true. This is based on the cosmological principle. And what is that? Universe is homogeneous on large scale and isotropic, right? So means in large scale it looks almost the same in every direction. So that is only things available. And we have the Einstein equation, and the solution of the Einstein equation is the Friedman equations. We know we do this in the cosmological course, and from there we know the universe is flat. K is equal to +1, -1, 0. So that is the only thing we can have analytical, and we can have the plot. Okay, but how that universe has been evolved? So there that is called. So there is a model called lambda CDM model. Lambda CDM cold dark matter cosmology. There is also one dark matter cosmology, but uh, that may be in the second talk. Okay, cold dark matter cosmology is the accepted model. This is associated with the dark energy. We all know this is around 60 to 70% is the dark energy, 20% is the dark matter, and baryonic matter is very less. Okay, why cold? Because the velocity is very less than the c. Okay, so that is why it's called the cold dark matter. This is the non-baryonic collisionless. Because collisionless, we can use the Boltzmann collisionless Boltzmann equation, right? And the baryonic matter. Once there is a baryonic matter, so then we have to use baryonic matter is collisional. So we can use collisional Boltzmann equation, right? So with this thing, so this is the kind of cosmological context we use, right? We have already talked about the CMB because this gives us the that. So this is basically the interaction between the matter and the photon. So that gives us this kind of variation. And we know this 3 Kelvin plus minus J because it depends on that, right? So this with these things we have this available. I'm not spending time on that because we need to, and we have already talked about this is the things we know. Simulation was what we will do basically rather than putting the equations. I thought that maybe so basic numerical set of equations basically, as I said, you have a dark matter simulation, right? One is baryonic matter simulation, another is gravity. Dark matter simulation means the collisionless component which they don't interact with each other, and this is basically your Friedman linear model. This is a differential equation. Basically, we are solving the differential equation. But this is a very solving the differential equation only through what is it called? Uh, I mean, first order, second order differential equation. Okay, we can easily solve it.
Yeah. In case of the fast dynamics of collisionless
Huh.
component,
Huh.
so you are completely considering neutral
Because there is no
hydrogen or
no G
something,
or nothing.
neutral hydrogen.
Because neutron can give the okay GR effect is there, but firstly we need to because this is the first time we are
Particle,
simulating the universe.
particle, yes.
Huh. So GR effect that correction will come say maybe later. Okay, but firstly because this is the first time the Volta string will have through millennium simulation the whole universe has been
What
simulated.
is the velocity structure?
We will see. Okay. So I mean the very first thing when we do the simulation, this is the way. So this is the thing we first need, right? This is basically the uh, 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 what is called the DVDD. Okay. So not okay. Another thing is need. So this is the collision rate. there is also the gas, right? So that is kind of the once we use the gas, there is a thermal energy, gravitational potential energy, radiation, chemical reactions, entropy, heating, cooling, all these things will be there. And another thing is that we have to also simulate the gravity. Gravity we just take theoretically, we just take the constant g, that is okay. But how do we put it? How the computer will understand? So there is a main of the work. So this is not my work. This is Volker Springer, Jagdish Singh Bagla. They have all done it in 1995. So there is a TPM method. So the people have now Padmanabhan. So this is the main driving force of the structure formation. Highly challenging computer. Okay. So basically these are the three things we need. Okay. Now equation wise you can get it from any book.
In case of that dark matter,
Hmm.
how you consider the mass of the
Mass of the they take only the mass of the say 10 to the every particle has 10 to the 6 coulomb mass.
field mass?
Because you don't know
Total mass you are considering.
total mass. No. Mass of each particle. Suppose you are working with 5 million particles
Yes.
or 10 billion particles and mass of each particle you know.
Mass of particle we know hydrogen mass.
Hydrogen,
But
yeah.
dark matter mass we don't have. Yes.
No, so that is why. So you are just considering say one dark matter particle is around theoretically it comes around 10 to the 6 for mini halo. Okay. For present day halo around 10 to the 8 solar mass.
No total mass we consider that
How many particles?
particles.
And 10 billion, handling 10 billion particles is very tough. Huh? So we understand, right? Right? Now, so this is a isotropic homogeneous. Okay, this is not my simulation, but these are all science paper from Naoki Yoshida. He is the man. I mean, who? So this is a simple state of the early universe. Okay, there is a you can say there is a little bit fluctuations. Okay, you know, it's homogeneous on large scale, but you will see. So they are basically we do the perturbation theory. Perturbation theory means when the fluctuations they grow, okay, and they grow and above the mean fluctuation when the mass becomes very high, it collapses, right? So that we know theoretically. Now we will see. Unfortunately, that video is not there, but okay. So simple set of now. So this is at redshift 100, much earlier. Okay, so this is the Tom Abel simulation 2000 science paper. Please see this paper. Citation is around 1500. All this paper citation is around that. Okay, so he simulated from z is equal to 100, then z is equal to 24. See, there are this is basically structure formation. There is some this perturbation grow and then form. There is some dense structure. Again, z is equal to 24 to 20, where the first star form. So there is a very dense region. So these are the kind of filaments. This is structure formation. When the small structure they form first to form the bigger structure. And if you zoom in, there's 24. At 18.2, there is a very dense region. So this is the gas. This is the site of the dark matter mini halo. Site of the dark matter mini halo. Okay, so here it forms. And okay, so this is a projection of gas density of 1000 simulation volume, approximately centered at the pre-galactic object, within which the star is formed. Star means the primordial star. So this is at redshift. So see, video you see how the redshift. Can you imagine from that redshift to okay? So when the first star is being formed. Okay, so this paper, Abel 2002 science, Tom Abel, he is from the Stanford, Harvard, and this is the gas distribution, the same simulation. Now we will do the simulation. So this thing to this one. This is the gas distribution at z is equal to 70. See the structure formation. These we actually we study in our cosmological. Okay, so these are all side of the mini halo. Why mini halo? Because mass is around 10 to the 5 to 10 to the 6 solar mass. Okay, comparatively small.
How this is that evolution.
No, redshift is been calculated means from the frequency. Like so the way we so for example when the photon is traveling, okay, so at every time it from the radiation it calculate that how much the wavelength has been increased or the energy has been so they and do that. This is a function of the radius. Okay, because that is the how we have to do.
Can you give any
Huh?
bright spot? Have any numbers?
Yes. So these are all 10 to the 6 solar mass, 5 to 10 to the 6 solar mass. So these are the all. This is 25 kilo per sec volume. 25 kilo per sec. Out of which this portion is only around say 300%. I will show. Okay, so this is 25 kilo per sec and these are all 300%. These are the size of the mini halo, right? Now if we just zoom in this side, so this is again Naoki Yoshida's 2008 science paper. Okay, so this is also more than 1000 citations. So this is just the zooming part. Zooming part. This is mini halo, 300% size. Mass is around into the 6 solar mass. This is the mini halo. Within this mini halo, so mini halo is still the collisionless, right? It's a potential well, within which the gas, the baryonic matter means only hydrogen from the recombination era and some electron, very few amount of helium, right? They are coming into the potential well of the dark matter, and they. So this is basically your that size is around of the order of parsec, 3 to 5%. So this is the mini halo. Within the mini halo, this is called molecular cloud. I mean gas, basically gas cloud or gas plums. Okay, which size is only 5%. See the resolution of the code from kilo parsec area you are coming to only parsec, and that can visual very nicely. Now within this molecular cloud, again this molecular cloud they collapse because once the gas is formed, it has a thermal energy which try to expand. There is a gravity which try to uh, right. So there is a balance, right? So once so there is that is called the Jeans mass. I mean when the thermal energy and gravitational potential energy they balance each other. Okay, so that is called the Jeans mass. This Jeans mass is around. So this is of the order of 1000 solar mass. The mass of the gas plums is of the order of 1000. You can calculate it theoretically because Jeans mass is a function of temperature and density. If the number density is 10 to the power 3, if the temperature is around 1000 Kelvin, you can calculate 200 Kelvin. You can calculate the Jeans mass of the order of 1000 Kelvin, and size Jeans length is of the order of parsec, 3 to 5%. Now this gas again collapse further because the star to be formed, the number density must be very high. So these gas plums again collapse, and then form the very star. So that star is around of the order of AU. Okay, say 6 AU or 270. So this is the from this cosmological simulation to we are here. This is for the primordial, right? So all these things have been so dark matter meaning molecular cloud collapse, and then from the photosphere, right? Now, what is the mass of this star? What is the mass of this star? Before 2011, people show the mass of these stars of the order of 100 solar mass. So people believe that mass of the primordial star has to be very massive, of the order of 100 or 200 solar mass, because the simulation was up to that point. Okay, so it was believed, and which means the primordial star, if the mass is around 100 solar mass, so it should not live longer because high mass stars die, right? So then 2011, that time I was doing the PhD in Germany. So Paul Clark and Ralph Plessen was my supervisor. They showed that once the very first star is formed, okay. For example, so you can understand if this is the radius, this is the radius of the gas plant. So we have a gas plant, and outside there is a mini halo. Gas plant is around say 3%. Okay. This is the gas plant, and these are the mass of the order of 1000 solar mass, right? And this is within a dark matter halo. Now we are not talking about the dark matter halo. We are talking about only the gas clumps. Now these gas clumps again collapse. Okay, this gas clumps has a number density 10 to the power 3. Number density. Now when it collapses, okay. Now if we plot, it collapses with a free falling collapse. Okay, so if I just plot the density, this is the number density, right? So at T1 the collapse is like this. At T2, okay. At T3, at T4, so the collapse has a profile, that is number density is proportional to R to the minus 2.2. This is the property of the collapse. This is a non-linear phenomenon. We have seen this collapse property. So here the number density 10 to the power 3, right? And the whole the gas collapse, the number density increase around 10 to the power 15 or 10 to the power say 14. So when the density, see the resolution, see the density variation 10 to the power 3 to 10 to the power 14, so almost 11 order of magnitude, right? So when the gas density, gas collapse and forming very dense region, when it reaches there, that time there is a protostar form, right? So which means the protostar form at the very center region here, right? Here. So this is of the, this has a size around 6 AU. So within this gas clump of 3 parsec, a protostar is formed at 6 AU, which has a mass around 100 solar. Okay, so that was the picture. Now, Paul Clark show that once the, because everything has the angular momentum, so this gas clump also has the angular momentum. Okay. Now suppose if there is a angular momentum, okay, and the entire thing is collapsing, okay, so which means it will form a disk, because the angular momentum will oppose the collapse, right? So if it is rotating and it also it's collapsing, so the entire these things will form a disk. So Paul show that the first star is formed, but it is surrounded by a massive disk, and the disk can also evolve. So if we put this thing as time is equal to t is equal to 0, then after 27 years, 62 years, see the gas evolution, and he shows that one this gas. So we also study the instability, because this is a highly nonlinear and there is a instability form. See the gas is evolving, right? 95 years, and at some locally, for example, at this point there is also local instability is happening. There is also chemical reaction is happening. Okay, because these are all hydrogen, helium, and there is a electron. There are more than 50 chemical reaction is going on. We can see every. We will come to this point. Okay, but the main point is that see there are also some local instability and forming a multiple stars. Now Yoshida shows that in one mini halo, only one star has been formed of the order of 100 solar mass. Paul Clark shows that no, what the first star is formed surrounded by a disk. The disk can also evolve from local instability and form a multiple stars.
Other than both chemical reaction, what kind of outside chemical reaction you
I will come.
Okay.
I will come. Otherwise, it will be.
Yeah.
Sorry. No, it's okay. So this thing is clear. That the main thing is that the primordial star is not only massive single stars, but he also shows that there is a multiple stars in a disk, right? So which means every star has some different masses, right? So instead of single star, we have a multiple star. Okay. Now this is in 2011. Then we have there are many sites. We zoom in many sites and see that yes, there are multiple star formed. This is in Hirano 2014. So here is the our basic definition of the primordial stars. It is formed within dark matter halo. It has a virial mass 10 to the power 6 solar mass, virial temperature 1000. I have already told that this is metal free. Okay, so this is the Now my work starts this simulation. So how we do that? Gravitational column of the primordial gas, which means this primordial gas, right? So how we do this gravitational column of the primordial? We are just talking about that basic things is very simple. There are two kinds of simulations. One is Eulerian, one is Lagrangian. Eulerian we all do like finite volume, finite difference method. These are all Eulerian. Okay. Now, thing is that suppose in Eulerian, what we do? Suppose there is a density variance, so we generally discrete it, right? And we see the quantity at this point. Okay. Now, suppose there is a very high density because you can see density. There is a lot of density variance. Now, suppose there is a very dense region here, very dense region, and just outside that there is a very here the suppose density are 14, but just the outside number density is very less. Okay, your code cannot resolve simply because it just ignored that. What we can do, we can you can make it small, right? So that at every quantity you can understand. So you can make it very small. So that you can calculate the quantity here. Now, if you have a let's say 5 million particle, your computer will take more than 1 month to because there are a lot of discretization. It will and suppose there is a no significant region here, so unnecessarily you are just giving time and right, which is of no use. Okay, because astrophysical is a very dense, very density variation is there. So you need those points where there is a very high dense region. Now what you do? So then Eulerian people they what do? They do the adaptive mesh refinement. So these are all mesh. Adaptive means you only select this region. Okay, where there is a dense region, you only select this region and only that region you do. The other region make it as it is. Okay, but again, there are, many small region you miss. So this is one type. You can also do with the adaptive mesh refinement. You can also do. It's a little bit. There is a lot of computational technique you need to know. So that your technical part. We are not going there, but I hope you have understood, right? And in the Eulerian, because the flow is going there, same flow, right? There is another called the Lagrangian method. Kind of, although there is a fight between these two groups because both claim that our method is the best method. Anyway, in the Lagrangian, so because there is this del T term, okay, so it's kind of we are moving with the flow. Okay, so if I take the loss of particle, just what he is asking, Somendra. So when there is a where there is a density region, automatically there are more particles. If there is a less region, there are very less number of people, less number of particles, and the dense region. So by the number of particle, the dense region means there are already lot of particle will be there. Okay, so that is kind of called smooth particle hydrodynamics. The hydrodynamics. So we call it smooth particle hydrodynamics. So this kind of two methods. So our this Ramsesson and Paul, so there is group is called this Lagrangian method. The entire the code which is called gadget. I hope you have heard the name gadget. Use this Lagrangian. So what is Lagrangian? We just come Lagrangian. Okay. Uh, Before we go to the theory, suppose Lagrangian use the. So for example, there are some particle is there. So how we calculate the density? It just take one thing and it consider a volume, which is called it use a mathematical technique called kernel volume. Okay, and it consider how many particles is there within this kernel volume, and this kernel volume can the radius depends on the how many number of particles is there. So it is adaptive, right? How many? So which means it take the contribution from every particle, okay, and the density within this kernel volume. That is okay. So, for example, any field, suppose this is a field, if this can be smooth with this, just this is a this. So this is basically your. So this W has a Gaussian. Someone take it Gaussian, someone take it some discrete value. Okay. So this is smooth within this kernel volume. So you can also this density, basically it's a averaging process. Okay, you are taking average from every particle. So for example, this one, same thing I have seen. It has considered, okay, this, and basically, so this kernel volume has a radius, say it has a density. So this is a radius h. So the volume is 4 by 3 pi r cube. R cube means pi h cube rho. Okay. So if there is a high density region and this is equal to how many number of particles, say there are 100 particles and the mass of each particle is constant. So this is a constant quantity. Okay. So which means if the rho is very high, h will be less. Right? If the rho is very high, h will be less. If the rho is very low, then h will be high. So this volume will adjust with each other. Right? Very simple. So this is the basics of the Lagrangian. It is smooth particle hydrodynamics. Basically, take the hydrodynamics, these mass continuity equations, and then you just smooth it, right? So this is why. So this is kind of averaging process. So you calculate the rho from the mass of every particle. Okay. The continuity, the continuous, you can just make it discrete how many number of particles. You just integrate it from j is equal to 1 to n. That's all. Okay, so 4 by 3 pi h cube rho is equal to n SPH. N SPH means number of SPH particles. So I have worked with 5 million particles. This, okay, and basically then you are solving this Navier-Stokes equation, this divinity. Okay, so while doing this computer simulation, there are a lot of obstacles you will get, but this is the kind of the basic thing. Okay, and you also equation of state, which because you have a entropy, you have a gas, so you have to deal with the entropy. So A goes to your. Okay, so we use this called the Lagrangian technique. So this I have used in my, and there is a more than 50 chemical reactions, but the major things I am talking about. So you have a in your gas, because it's a primordial, so we have a hydrogen, some deuterium, helium, and electrons are available. Okay, now we know that generally the metals can cool the gas, right? Metals can cool the gas, but that time there is no metal, only hydrogen. So how the, and suppose thermal energy and gravitational energy, they balance each other. If they balance each other, how the gas will collapse? It will not collapse, right? Gas can only collapse if there is some coolant which can cool the gas. Then only gravity can can be active, right? Because initially thermal energy, gravity, they oppose each other and come to a balance. Again, if the gas is cooled, then only the collapse will continue. So the cooling is an essential factor for any nonlinear collapse, right? So here how the gas cools. The gas cools at the, people have shown this is the this work has been done in 1970s uh, by Richard Larson. They have shown that even our Shaha, so they have all, so these things have been implemented later in primordial, but these are the reactions. They have shown that hydrogen combined with this electron, they can emit radiation. Through rotational emission, vibration in the quantum state, in the rotational emission, vibrational emission, it can cool the gas. Because so, which means once the atomic hydrogen to molecular hydrogen is formed, due to rotational and vibrational emission, gas can be cooled. Okay, but that cooling is very less. I mean, that can cool the gas around only 200 Kelvin. I first show you the picture. Then I think then it will be. I thought that I will. It is not needed. But This number density I have already shown you, right? Huh? Uh, Here. So this is a complete picture. So right now we start from here. 10 to the power 3. Number density 10 to the power 3. This is the number density 10 to the power 3, right? From here. Forget about this left part because this is cosmology related. When the mini halo is formed, mini halo, that time the virial temperature of the mini halo is 1000. Okay, virial temperature of the mini halo is 1000. When the gas comes into the mini halo, it also has a temperature of 1000 because it will be shock heated. Right? When gas is coming into a potential well which has a temperature of 1000, so of course that it also have a 1000. Now when the 1000, that time this rotational vibrational emission, I mean due to transformation of atomic to molecular hydrogen, the gas can cool up to 200 Kelvin. See, this is around 200 Kelvin. Okay, and then temperature is increasing because of the when the density is increasing, temperature is also increasing because that time three atomic hydrogen, there another reaction happens that is called three body H2 reaction. Three atomic hydrogen they form to molecular hydrogen. So that is a gas temperature is increasing, and when the star is formed, gas temperature is around 1000. So now I just go to the hmm. So the gas, okay. So at high densities, there are three atomic hydrogen. They form this molecular hydrogen. This reaction, people have seen that this is actually very fast reaction, and by this reaction, almost all the atomic hydrogen they form molecular hydrogen. But now, once the molecular hydrogen is formed, of course the gas is cooled, but at the same time, there is a 4.4 eV release of the electron volt, right? We know from the basic physics. So it can also heat the gas. Release of 4.42 electron volt. So that can heat the gas. At the same time, when the gas is collapsing, there is also PDV heating, right? PDV heating. So which means the cooling, there is also dissipation heating because three hydrogen forming this one and the back reaction is also happen, right? H2 also form that which is called dissipation, H plus H plus H. There is also collisional induced emission. Okay, right? Now the same reactions also happens from helium. So there are other reaction also. So if you just go to the science paper, this around 50 reactions are there. All these reactions are there in our book. So this is I have not done. There is a chemistry group because you understand there is a chemistry group is also required. Okay. So ultimately, but these two reactions also this is at low density, this is at high density. Okay. Gas can cool faster than the free fall time. Numerous reactions, primordial chemical network. You can see this paper. So it has H, H plus, H minus, H2, H plus, He, He plus, H plus, D, deuterium, D plus, D minus, HD, HD cooling, HD plus. Now you can make it correction. There are other cooling. Vimannath also is working on that. Okay. So there is a collisional ionization, recombination. I think we answer your questions, right?
Yes.
The collision ionization, recombination, radiative cooling,
What about the
photoionization.
deuterium abundance?
These actually I don't know much. I mean, people. So the contribution is there, but very less.
Minus 5 something sign.
Is there? I mean, it contribute also, but I mean, you can have some research on that how much it contributes. But more or less, say for example, maybe it will be 200 to 250. Okay, but these are the kind of the major things. I mean, at the very basics we can, but these are there included in the code. Okay. Now all these things we have included in our code, and then there is also like rotation. So till now there is this is chemical reaction. This is one part of my thesis, and another part is that rotation, the angular momentum. So because every halo has the angular momentum, right? This how this angular momentum we have done it by rotational energy and gravitational potential energy. Rotational energy we can calculate the basic physics and the gravitational potential energy. And so this is called the parameter beta 0. Now we have put beta is equal to a different, which means this is at 0% means no rotation, 0.5% rotation, 0.7% rotation, around 20% rotation. So we have a different range of rotation of the halo. So some halo, I mean some clumps, not halo, some clumps is rotating very fast, some clumps is rotating very slow. How these things, because it affects your the final result, right? So you have to okay. You understand? So this is the rotations of the halo. So this is different by the beta parameter. I- Artificial halo, cosmological artificial halo means you can take these laser clumps 3% and put these things, or you can also have a cosmological halo. I mean, in the cosmological, you can take that clumps from the cosmological simulations. Okay. Now I will not. So this I will only show the results. So these are the kind of the basic. There is another technique which is because this is the technique by which actually simulation was possible. That was called the so once the star is formed at density number 10 to the power 3 to 10 to the power 14. At which point you will consider that this is star because gas is collapsing. When the gas density reaches around 10 to the power 14 number density, that time you consider it as a sink or as a protostar, right? So that is called the sink particle. Small, high density, gravitationally collapsing region that can accrete. So once the star is formed, we can consider that that is the star. So it can also accrete matter from the and because it is a star, it is now it cannot be considered as a gas, right? Now it must be separated from the rest of the simulation because you have a gas simulation. One the gas collapse form a very core. That's why we call it sink. So now it is we have to consider separated it from the rest of the gas so that the rest of the gas can be again evaluated, evolved, can be evolved, right? And this sink is kind of protostar which can also accrete matter. It can also radiate photon, right? So all these things till now we have not considered the radiation. Radiation is my now current word. Now it is accreting the matter. Okay, so this is for the thin particle technique. So this technique was given by Bate 1995, and we have also considered it in our my student Raghuvanshi and Dutta. So all these simulations we have included this modified gadget too. Chemical network, thin particle, unstructured maze, primordial, around 45 chemical reactions. So these things first we show it in the Japan conference. So we got this poster prize talk for that. Okay, so that was the first thing, and then when we now you will see that this is my simulation from here from the gas plums. I mean these plums to how the star is being formed. So gas is collapsing. This structure is forming because of this angular momentum, which Clark shows. We have modified it and we have included all these things. So that's why it got the best poster. Okay, and ultimately see these are so it's a lot of star has been formed. 2%, 2% to 500 AU region, and all every star is have a around 6 AU. See, every star has a inch mark around 6 AU. This is the radius of the star and the mass of the star, right? Now again, now then just these are the so
Your mass will be the groundwork.
but it is the initial mass, but again quickly it acted to matter. So the when you evolve the gas, it will see that there is a range of mass. Now only the papers because
Mass of
mass of protostar, right? Exactly. Now in 2015, so that was in 2012, and then just the paper. Now what we will see? Now we change the chemical instability. I mean, if some gas has some more number of hydrogen, if there are more number of hydrogen, then there will be more cooling and heating, right? There will be more hydrogen formation. Other chemical reactions will change. So we have seen, we wanted to show how the chemical imbalance can affect your final INF, right? Because all these things we don't know. We have to do and see. We have seen that, for example, two halo, we have taken halo 1, halo 2. Halo means meaning halo 1 and two different meaning halo, and we have changes this chemical. So this code, just constructing this code, it takes just 3 years. Okay, and There are lots of debugging all these things. But once it is done, and now we can play with that. So there are many chemical you can due to chemical imbalance see the final structure. Another thing, this is the when the star is formed. I mean, we consider that this is time zero. Now, once the star is formed, then we see the rest of the evolution, which has not been shown before. And we have around 4,000 years. Previous all the simulation, if you remember, Clark simulation has done only 90, 110 years from the first star is formed. I have done up to 4,000 years. Okay. And this for and see the only this thing is the chemical imbalance. Instability has been changing. Okay. So this is with Vimanda. Then there is this is with me, and this is with Vimanda. Again, this is in MNRS. See how the number of things are changing. All things are changed. Only the due to the mm, uh, how the reactions are affecting your final. Because even the number is 5 or 10, but it is so important because your next generation star depends on the how many zinc and how many zinc means how many protostar and what is their mass. Okay. Uncertainty. So this is a completely uncertainty in the three body H2 formation rate leads to the difference in the chemical state of the gas as well as the disk fragmentation. That is called the this process is called the disk fragmentation. Disk fragmentation means disk is being forming. There is a protostar surrounding disk is there. Disk is being evolved, and also there is a local instability which has been done by Tumre parameter, right? Again, so every time once the density has been reached to that part, this part is called separated itself from the rest of the gas. The entire process is called fragmentation. So the disk is been fragmenting to form a multiple system, right? So this is exactly we have done. So the chemical uncertainty in the chemical this three body H2 formation leads to the difference in the chemical state of the gas as well as the disk fragmentation. Then in the next 2 years, we have been the second part of the physics. It was the angular momentum. How the angular momentum, so the low angular momentum, higher angular momentum, how it is affecting our fragmentation. So my main thesis is that how the initial conditions affecting the our final system. So here one interesting thing we found that so this is the for example the green is the higher angular momentum. Okay, blue is the low angular momentum cloud. This is the initial state. Initial state means when the number density was here. After collapsing, you will see even the low angular momentum, higher angular momentum all have a same profile. All have same profile. Even if the higher angular momentum clump and the low angular momentum clump, after the collapse has been reached here, all have a same profile. Which means higher angular momentum clump, gas cloud, they distribute more angular momentum once the star is formed. Okay, so which means there is a distribution of the angular momentum during the collapse because all have the same profile, and that is because
I have. Do you find any time difference
yes,
from the
yes,
start to
yes,
collapse?
yes. Higher angular momentum clump, for example, in my simulation, higher angular momentum because it's a higher angular momentum, it opposes the collapse. It took around 1 month. And the low angular momentum means it quickly collapses. It took only say 1 hour. But the higher angular momentum plants, it took almost 30 days to run. And if you just plot it, so there is a almost 1 order of magnitude between the higher angular momentum cloud and the low angular momentum. Because there is a no rotation, so it just collapses. The higher angular, if you go for higher, and there is another thing, low angular momentum clumps means it just collapse from all directions. So there is a possibility of formation of a single star only because there is no disk. But higher angular momentum, they have a disk-like structure. They have a more number of protostars. So there is a lot of difference.
Of the pocket is
Huh?
Tumre
Tumble parameter. So the disk can okay. There is a range of masses. So that is why so we have taken from 0 to very high. So this is in 2016 in later, and the angular momentum has this profile. Another thing is that higher momentum has a distribute more angular momentum. This is the point. Then there is another in A and A. So this is the kind of you see the gas distribution. The disk is see the star is coming. This is the low angular momentum cloud. See, this is very centrally condensed. Centrally condensed. And okay, so this is in 2000 area. See, 2000 area it is much bigger. But this is very centrally condensed. See, as beta is 0.2, 0.1, much disk like structure. This is just very small. Okay. Now here it's an important thing. This is the third one, which is during my postdoc. Now if we so ultimately there is a multiple stars, right? Now if we plot all these things, just consider the radial velocity of every star. The radial velocity around 20. Minus means just direction. So within 20. So primordial star all have a velocity say 0 to around 30. Okay. Now just we have thing in mind. Let's compare it with the escape velocity. It's a potential well, so it has a escape speed. When we compare it with the escape velocity, what is happening? This is the escape velocity. So there are some stars which have been escaping from the system. Escaping means so star has been forming here, escaping from this system. It's just like rocket is escaping from the Earth, right? Some star is escaping. So if you consider it, these are all high angular momentum cloud. Most of them. These are escaping. Of course, you will be interested. What is the mass of this all these stars? Okay. So can we? Okay.
At last I will be interested how many percentage are escaping the system.
Exactly. That is the question we wanted. Exactly. How many? Number is very small. Exactly. That is exactly the question we wanted to answer. Okay. And what is the mass? Huh. So these are the we can consider the mass of each star. What is the estimate? Only few. See, for example, YOLO is CH2. For example, mm, this one is between to 0.1. The very high angular momentum cloud. High angular momentum cloud means the big disk, hydrogen, the big disk are there. Okay, the star has been forming at the very outer part, and they are escaping. See, for example, 1, 2, 3, 4. Okay, this one only it is a 0.7 only. So, okay, now the point is that how many and can we find those stars into our Milky Way galaxy? Most sophisticated 3D simulations are able to follow. Now, if we wanted to evolve the stars, so what is the evolution of our universe around 13 billion years? So, so to see the stars, you need to run your simulation for 13 billion years. 13 billion years. And we have been able to run only up to 4,000 years. 5,000 years. And you have to run for 13 billion years. Okay. So which means because simulation has limitation. Of course, I mean 4,000 years is even much bigger. But to see the evolution of these stars, whether the star is living or not, you need to for 10 billion years at least. Okay. So most sophisticated 3D simulation are able to follow evolution for only few thousand years, not sufficient to estimate the final mass of the protostar to the gravity. Even the most sophisticated simulation also can't do. So the next we judge it, then we think a alternative one, semi-analytical or semi-numerical. Okay, what we do? So we just took. So we know. So what we know? We know the radial velocity. We know the mass from here simulation. We don't know the mass. We know the radial velocity. We know the rotational velocity. We know the temperature. We know everything. Put these things into a semi-analytical model or semi-numerical model. Just simple Newton law, nothing else. Okay, D2 or DT2, D2, it's quite interesting to me. It's very simple. D2 5, D2 D2 or DT2. Okay, because we know, so every star will follow these things. But here, there are some protection you have to take because stars are moving. but stars are moving where? In a gas medium, because there is a gas outside, right? In a disk. So there is a disk. Think about stars are there within a disk. So there is a gaseous medium. So when a star is moved, also, of course, it will have a friction with the gas. Okay, this star also will accrete matter from the surrounding, right? So you need to have a accretion equation. This star also will radiate photon, right? The dynamics is only given by d2 by dt2, d2 by dt2. That is okay. Angular momentum conservation. But then what is the accretion, which is accreting matter? It is radiating matter, right? Then there is a n body. If you put the Newton law for a n body particle, right? So this to give dynamics. This is giving just the, it has a sound speed, so it has a the friction. You can just calculate it. This is the scaling relation. So now we don't know, because this is a semi-numerical only this portion. So we know the what is the accretion rate. So we consider the Bondi file rate. Okay. So you can also work on that project. So this is the five first order differential equation DMDT, because this is the standard accretion rate. Okay. And you have to also calculate this. This is a so nice and simple, but extremely significant. So that was first. This idea was given in the Astronomical Union proceeding 2018 Italy, and then we solve it using the RK fourth order method. Okay, RK fourth order with compressible flow coupled with gravity plus drag. Drag means the friction. Requires a very smaller time step. Now here the time step solving the differential RK4 method, the time step is so significant. If the time step is not stable, the result will be different. So we use a CFL condition. Today CFL condition. I mean, you can just check. So this will give you the stable time step. Okay. So with these things, so we just publish it in FJ. Okay, with Sharonno, Athena Stacy, and Jhusi. So we see, so here just see. So there is a different velocity from up to 20 kilometer velocity. Okay, we have a rotational velocity, radial velocity, mass, initial, everything we have taken from the gadget to simulations, right? We have taken everything from here, right? Then solve it for T. There are two type of. So this is the distance versus time. So we have around 10 million years. Okay. See, the green stars are actually roaming around. See, within 1,000, so it highly matches with the simulations. Within 1,000 years, it is roaming around. So these stars and red stars, they are escaping the cluster. Red stars are escaping the cluster within 10 million years. So we don't have to go for billion years. When within million years, they are escaping the cluster. And some stars within few thousand years, they are actually roaming around. Okay. Ah. And we have also plot the accretion rate. See, the stars which are escaping. Escaping means when it escapes, there is no gas, so it cannot accrete. Accretion rate is very small, 10 raised to 9. But for the green, the accretion rate is very high, around 10 raised to minus 2, 10 raised to minus 1. Which means the stars which is forming inside, which is roaming around, they can be very high massive stars. But those who are escaping, they can be very low mass. So there is a possibility that this low mass star can be survived for can be evolved for 10 billion years, right? So this is very okay. And after that, Shukalpo, one of my students, he was doing, now he's in Italy. He included the radiation. So in my work, so there is no radiation. Okay, it was only accretion. Now he included the radiation also with L is equal to GMM dot R. Okay, which means accreting also radiating. So there is a encounter, right? Inclusion of radiative feedback in the semi-analytical model. So also he used the rotation of the clouds. So there is a, for example, a star is moving in this direction, gas is also moving in this direction. Then there will be summation. But if there is opposition, okay, so we are taking the effective rotation, so which is giving by Vx minus Vx gas, Vy minus Vx gas. You can do it either in Cartesian or in polar coordinate. Okay, so he included that, and so this is the kind of a X Y. See how the stars is moving in a plane, right? Reds are escaping. See all the groups are how they are. So this is exactly we just see in the simulation. You can visualize the stars are moving inside the center, right? And there is a final mass, and final mass change with the radiation factor. So F is a parameter which can give how much radiations. So you can see. So basically, see mass of the star may be 10 solar mass, okay, or maybe less due depends on the radiation. For example, here also, okay. Hmm. And radiation also have this. I think you understood because the time is also okay. And recently again I have done the simulation with Raghuvanshi, another student. We have done this rotational simulations again, but in a much modified, much better way, and for much beta is equal to 0 to beta is equal to 1.5 continuous. Okay, and this is the recently published in Astrophysical Journal. This is the temperature evolution. This is the density evolution. Okay, and when just last thing, when how many stars are being ejected, very less. And if you calculate that, is just the back calculation, if a star which has been formed after the Big Bang, if a star has been, if a star, if can be seen now, what will be the mass? Theoretically, you can calculate the, if a star has a mass around 0.8 solar mass or less than 8 solar mass, then only those there is a possibility that those stars can be survived till now. In our simulation, we have found there are only two stars. Uh, which have a mass less than 0.8. A few things can overcome strong gravitational drag of the dense gaseous medium and move away from the star cluster with radial velocity greater than escape velocity. Only 10 to 12% low mass sink less than 0.8 solar must stay in the main sequence for billions of years to survive the here. So I think, and there are, so I have a fortune in HRI. I was fortunate enough they allow me to supervise two students, and both the paper has been Sukalpa and Raghuvanshi, and now two more students are working. Okay, so these are the project, very defined project. I mean, if we work, so now actually with Abraham Loeb we are just working formation of the black hole. The another important part. Okay, this star is a, there is a possibility that this star can survive as a low mass star, right? What about these stars? They may form a black hole. They may explode as a supernova. They may form a massive stars, right? We have to see with the addition of the physics, we can again see what is the fate, ultimate fate of this star. Okay, so with Azure we are doing that. Then another thing is that this radiation feedback we have included in semi-analytical model. I also wanted to use it in the simulation, the gadget to simulation. And as I said, it is a black hole supernova or merge. There is a, you can work also on that model and just include the merging condition, right? Okay. And how the metallicity is what I have not even started, but the metallicity what is another, those who are working with poor metallicity. There is observations. I am also working on one observational this thing that the poor metallicity starts. For example, you have the HDSS data available in the internet. You can just, there is a many EMP very poor metallicity. You can just calculate the gravitational. Uh, I am. I can continue, but you showed me for 5 minutes, so. Uh, so these are the um, uh, uh, as I said, just those data is available. Okay, so you can just check with that, and you can include this gravity, surface density, okay, surface temperature. You can calculate the logarithmic of g, log g to c. Okay, so that you can see that some of the stars actually there is a very poor metallicity stars they are there. So poor metallicity means they have formed poor metallicity, which means they have formed at that point, right? There is another thing, like for example, this one. Okay, uh, this one. See, for example, this is, I mean, this is of course the prediction that low angular momentum cloud, they are very centralized. So of course there is a possibility that low angular momentum cloud form a black hole in the center or very supermassive stars, because formation of the super, so there are many aspects formation of the supermassive stars. Okay, if you just consider the it can form a black hole. Okay, so then what you have to do, you have to just put the Schwarzschild radius, the GR effect. Here you can actually improve that. You can also calculate for the supermassive stars, the number of radiation photon, number of photon and you can calculate. Okay, Lyman Warner photon, right? If the supermassive star, if there is a low mass stars, if there is a merging, and how far they can go, whether the low mass stars are actually just going away.
Mass function, right?
History of the mass function is there, but I choose not to show it because it's still a semi-numerical simulation. Okay, and I can
You
show.
have an approximate.
I have approximate, but I cannot tell because it's a talk. So I cannot because there are two type of mass function. One is salpeter. Okay, huh. So because it's giving a semi but the I
Yeah, one debate is there. Already observation found round block they can calculate.
it's the actual observer of download here.
Yeah, it's a there is a peak. Salpeter is there. Another peak, some kind of support.
Low master actually many people are saying that low master are
0.6 is the natural
natural.
peaking.
But there is another.
Observationally, it's
Maybe they are very close, so we don't know. So this is the kind of summary, and these are the Shobhan Mokshi, who is now pursuing PhD. So they are the students. Shubham Mundu, now he's so here I was postdoc here for short period. Shubham Mokshi, now he is moving to Max Planck, Golden Pal, Saurabh Dhania, and they are my collaborator. Also. And these are the teaching experience I had, PhD course at HRI I have taken in last 2 years. So this is the official.
Do you have any plan to add magnetic?
That's a good, very good question. Yes, the simulation. Even in that,
What time or what rates you would add?
the magnetic field, you first need a seed for the magnetic flux. Okay, or magnetic field. Actually, some people have already shown this magnetic field can be amplified. Okay, and this amplification of the magnetic field can actually affect the collapse significantly.
Since you are adding rotation,
Huh.
the magnetic field also coming.
So we'll do it by step by step.
But it is too complicated.
No, because if you have a turbulence magnetic field, I mean it can have a because it will easily.
Your the equation
Uh,
significantly change.
Now, one problem in the gadget,
velocity profile,
one problem
particularly.
in the gadget is that it is del dot P is not zero. That is the problem. In gadget 2 you can't do, but with other things you can do. But yeah, there is a Federer, even Sharon No, they have worked on this magnetic field. I have also a plan, but first I need to be stable.
Yeah, and I just wanted to initially describe three processes. Mainly we talk about the normal magnet. What about the other things? You have
Because
got
other things people
mentioned?
have already shown there are lots of that.
Lots of
That you start with the isotropic and you end with a.
yeah, it
So
will
there
go beyond the cosmology. It will go to the
beyond.
cosmology.
Then there is
Yes.
nothing. I mean,
Yes.
ultimately
Yes.
you will form a dark matter. That's all.
That's yeah.
So the
That's it.
but how the star has been formed. So that's why people
No, it's
people
more,
only.
more relevant for us at least.
Actually, so that's why the cosmological simulation, but that's all. After that, people just don't start with this periodic matter. It's a non-linear phenomena. There are lot of chemicals, lot of
Yeah,
radiation,
lot of unknown.
unknown stuff there. How the
They
star
can
has been
predict
formed.
anything. Yes, right. But here you have your observations support.
Exactly. And Rafael Snyder and their they are all working on this observation. Means if we can very cool mineral star. And the PISA group is SNS, School and Operations Theory. They are doing
Yeah, I think slide number 27, you showed the chain of, you showed the deuterium and helium also.
huh.
So this is population stars, and before start, what is the possible source of helium and deuterium?
See, main thing is only hydrogen. Because helium and deuterium, these are, I am just saying it because it's a chemistry group, they have included all these things. Contribution is very less. Very less.
No.
HD
The
cooling
one
is there.
question he might be yeah. Formation of the helium, you need some hydrogen, right?
Yes.
Unless
So that's
some
the
fusion
Huh.
hasn't happened.
So that is why initially hydrogen start, but when the collapse, when the collapse is there, temperature is increasing.
Yeah.
So there is a paper on that. I have so when the temperature is increasing, at some point helium reaction will start, right?
Temperature is sufficient. Helium you need high temperature. Yeah, temperature high.
I think here helium
Fusion is yes, fusion is of the order of
five,
5-6
huh.
million Kelvin.
Yes.
No,
So before
no,
helium
that
gets
that
formed,
you are with in the initial gas, there are few heliums are there.
helium are there. That is from that helium reacts. Not hydrogen to helium.
Not fusion.
And
Electron capture.
I mean, it is impossible to think about what is forming inside the stars. We are
Yeah,
not even
that
talking
is-
about. So
yeah,
that's
that
a
is
mark.
different.
That's-
That is, we know that it's helium, hydrogen is converting to helium, helium to others.
even just to resolve these things up to 6 it's also extremely difficult from that kilo per second.
If some stars I mean, still are
There.
there, present,
Huh.
in which form you can expect?
Which form that
White dwarf, not black dwarf,
Mm.
brown.
round of many people say that they may be you have to actually consider it from the main sequence. Because when it escapes, we have to first think that if it entered the zero age main sequence, jam stage, right? Only if enter the main sequence, then only. But see, this is still a vague statement because I am not using any chemical reactions there. Okay, it's just a theoretical calculation. It may form as a because these things we don't understand. But the one thing, see, there are only three, four papers which says that we have observed extremely poor metallicity stars, which means they exist. But out of say 200 billion stars, only you say only 10 stars is poor metallicity. And also, how do you observe poor metallicity star? ah,
Globular clusters.
Globular clusters have
Some of the
exactly.
stars you already
Already.
reported have a really extremely
In 10 raised to minus 6, say 10 raised to minus 5. And actually, globular cluster we found above the disk there are some.
Said that consistent with observational signature of extremely metal. What are the observational signature of
JWST. There are
what kind of observational signature?
as I said that HDSS they have found very extremely poor meteorological stars. So if you just plot the surface temperature, taking surface temperature and surface density, you can see the this. I just forgot the name, that term. Log G versus which plot? Log G versus. From there you can actually, from here also you can calculate and match with that this log G versus this
Metallistic.
Metallistic. A by A by
yeah, Fe by H,
Fe by
H by H.
You have to find the geometry.
Geometry. And so there are those things are there. You can just click and see, just play with
And
that.
snatch the novel.
Fe by H.
Sir,
Hmm.
how many protesters have you found from 1 million?
How many protester can be formed from?
1 million. That's a different mass of this.
As I said, some simulations say that in 1 mini halo there will be one massive star, which now is actually the same. But if there is a disk formed, disk fragment, then it is a multiple system like present day star. Okay, so that's why I told. Ultimately, semi-numerical shows that actually two type of stars is there. If some escape, then it will be low mass. If some roam around, then it will be massive star. So our simulation is the first things that shows that. So previously there are two groups. One shows that no, only massive star is formed. Paul Clark shows no, only multiple star is formed. We have shown in a very tactically, actually two stars of forming. Someone is escaping that has a low mass, someone is roaming around that has a high mass, which can give quite
Yeah.
a good. You have some more questions, or he will ask a question?
No, no.
Ah,
No, you continue.
ah.
It's,
Oh, yes, yes. Yes.
yeah, means whatever the density, you put some limit here.
Hmm.
Yes. It's self-understand.
Hmm.
To put the much
Yes, you
higher
can do.
density.
Yeah, you can do. You can do.
You can do, when you come up with the same things, because our most of the people believe that initial stage we have only massive stars.
Right.
Now means yeah, of course we believe that massive stars and nova stars form in the cluster. But firstly, initial case
See.
we thought that only massive.
What is the? So that's why we only call sync or proportion.
Yes.
You have to give some point. So which point you will give? You can just don't give arbitrarily. So the only thing we have only genes, right? Only thing is the genes. You can again, you can in fact do that one. I have taken this as a thing. If your simulation allow, you can must go further.
Say that it for a year.
18.
80.
You can go.
Still things will
Provided,
work, yes.
provided you can resolve that. If you can't resolve, the physics will not be that much different.
The technical problem.
But you will end up because you can't even resolve it. So that's why it is better. You can consider it as a see. Start from at 10 to the 24. The density of the star is around 10 to the 24. That right number density. Here you can't go. So that's why you consider it photostar. The good thing is that photostar you can again evolve the photostars. The accretion, radiation, even Takashi Hosokawa in 2011, he only does the radiative hydrodynamic simulation, and he completed in 2D radiative hydrodynamic simulation. He just definitely answered the question, the mass of the star is around 41 solar mass, because he shows that radiation can evaporate the entire disk. Ionization is happening, evaporate the entire disk. The star is formed in the final mass is 41. But that is only a specialized, I mean, in one case, but you have a multiple stars. So you can, what you can do here, because you can try. For example, in this is my simulation, and my student Raghuvamshi, he has done it 10 to the 15. But not that much different. As I said, for example, this is my simulations. Okay, this is my simulations. Okay, 10 to the 15, and this is his simulation. You understand the entire?
These are star formation.
Now what do you now? Have I?
Many people what here in the star formation. So must have tried.
I have a silly question. All you start with dark matter hello. What do dark energy?
No idea. No idea.
Leave 70% of the.
Because that is not my area, and that we don't understand. That is the energy people are there. See, you can give many abstract for dark energy. This may be, this may be, this may be. All are maybe. Even some people now question the Big Bang cosmology, right? Because there is, it's not as last 30 years they are fighting. See, I myself work on Big Bang cosmology because I have to. Otherwise, I believe the null gets theory, steady state. Ah,
Yeah, that is the first star is
Yeah.
fantastic.
so that's
there is
why.
your observation
That's
basis.
why we don't want. We just take the cosmological principle. Universe was isotropic, perturbation there, entire simulation. I mean, the collapse.
There
That
was
is there.
some result from Planck that CMB is not isotropic, but I don't know exactly.
CMB is anisotropic. CMB is anisotropic. Planck
You
has
start
already-
with the
Yeah.
isotropic, then
No, no,
can
no.
you create that anisotropic? CMB.
The anisotropy is coming from the fluctuations, right? The interactions between. No, ultimately,
Remember one side of it.
no. All the simulations is coming. The initial condition is CMB, so which is the anisotropy. So that's why you are giving this anisotropy. Fluctuations.
Anisotropic means fluctuation with respect to some background. That I don't know, maybe I'm wrong. I heard a talk that was showing that complete different temperature in two sides or something. Or something in here, this or that.
People are.
What about the competition facility? How do you
You need a cluster.
you use that?
Exactly. But now actually if you last 5 6 years or 10 years, I think now India has a lot of, so these things actually were missing. Now RRI, HRI, um, now people have realized that we need one. But at the same time, it's very difficult to maintain. For example, in Aizar Mohali, it just crashed. No one.
We have
Because facility, I need a facility. Otherwise, I want to lie the. So we like to.
but it is also applicable for the outsider also. If outside,
So these all work in the acknowledgement. These are all HRI. And previously, Aizar Mohali was working, but now it's not. But we have a Pune, we have a ISP, ICP, so they have.
Jayanta in Muali, right?
Hmm?
Jasil Batra is now in.
Say
he retired or still
No, no.
serving? Yeah. That then retired.
Maybe in 50s.
Okay, yeah.
152. Thank you
Thank
very
you
much.
very much.
Thank you.